Hey guys, the objectives for this video is to look at the relationship between TV, dimensionless time, dimensionless depth, Z on H, and U. We're going to define these in a second, and then we're going to do an example. So, we already know dimensionless time from the previous video as CV times T on H squared, where H is the drainage path. The next thing we need to define is Z on H. Just to show you why we're going to be defining these factors, we're going to be using this graph, which looks like this, which has dimensionless time on the curves, which has Z on H on this axis, which is dimensionless depth, and has U on this axis. So we're going to first define all these things. So Z on H, Z is the depth we're concerned about, so the depth we are looking at, and H is the drainage path. And this is obviously dimensionless because you're dividing meters by meters to get just a number. So just to do a couple of quick examples just to show you what I mean. Say we have one-way drainage. Okay, so we have a one-way drainage case. And let's say that we are looking first of all at a point which is at the center of the layer. So the center of this layer, so over around there. So if this was, say, okay, because it's one-way drainage, that total distance is H, and we're looking at the center, so we're going to a point Z from the surface. So you can see just graphically that Z on H would be a half, right? Z is a half of H, so Z on H would be a half. I can show you this with numbers. Say H was 8 meters, and that means that Z would be 4 meters to the center of the layer. The Z on H would be 4 on 8, which is 0.5. So if you're ever confused, you can always just make up some numbers to see what's going on. Let's say we were looking at a point which is at the bottom. So at the bottom of our layer. So Z now would be the full 8 meters. So we would have 8 on 8. So Z on H would equal 8 on 8, which is 1.0. So I could do this for every single point in this region if I wanted to find my Z on H, which is this axis on our graph we're going to be using. And this is just for one-way drainage. So we were doing two-way drainage. So I'm going to draw up the same situation. But now, because we're doing two-way drainage, our H has been halved. So our H is only 4 meters. So H is 4 meters. So say, once again, we're looking at a point at the center of our layer. So Z from our surface would be 4 meters. So that means that Z on H would equal 4 on 4, which equals 1.0. Or you can just see it visually. Z on H is the same number, so like graphically it's the same. So Z on H would be 1. If we were looking at a point on the bottom, so we would be coming down here now, so our Z would be 8 meters. So Z on H, Z is 8, and H is still 4, so it's 2.0. And you can see that's at the maximum value on our graph, 2.0. So you can do this for any point in our one or two-way drainage case, any point inside here. You just need to find Z on H to be able to do this. Now the next thing we need to discuss is this value U. So U is equal to the change in effective stress over the change in the total stress. Now we know that effective stress is the same as total stress minus the pore water pressure over the change in the total stress, which we can then further rewrite by splitting up the denominator as 1 minus the change in the pore water pressure over the change in the total stress. Now we can redefine this, the change in the pore water pressure, as the excess pore water pressure. So that is the excess pore water pressure. And this is the applied load or stress, so the applied stress to our system. Okay, so now we're going to go do an example to see all these things in action. So let's say we had a applied stress. So the applied stress is 60 kPa. So we've applied a stress of 60 kPa. We want to find the excess pore water pressure. So we want to find the excess pore water pressure, which is obviously that term there. And the stress applied is 60 kPa would be the change in the total stress. That's the applied stress. So we're given those two things. We want to find the excess pore water pressure when 60% consolidation has occurred. So when 60% of the settlement has occurred. And we are looking at a point in the center of a soil layer, and we're going to say we have one-way drainage. Okay, so using this information, we're going to obviously use this graph, because that graph is in terms of, we're going to be finding this change in pore water pressure. That's the aim. So we're given Z on H, so we need to find Z on H and TV. So let's quickly find Z on H. So if we're looking at a case which is one-way drainage, so the entire length will be H, because that's the maximum drainage path, and we're looking at a point in the center of the layer. So just graphically, Z on H would equal a half. If you want to think of it as numbers, say Z was 2 meters and H was 4 meters, that would be 2 on 4, which is a half. Okay, so Z on H is a half. We now need to find TV, so we can see which line we're on. So to find TV, we're going to have to use the graph we saw in the previous example, because we're given a settlement of 60%, so 60% settlement has occurred. So we would have to come across at 60%, come across to our number, so hit that curve, come down, and we get a value of 0.3. So TV, so we found now that TV equals 0.3. So we have Z on H equals a half and TV equals 0.3. We would then come across to this graph. So Z on H is a half and TV is 0.3. So we would draw a line from 1/2, which is here. TV 0.3 is on this curve, so it would come intersect there, and then would come down there, and we get a value of about 0.62. Call it 0.62, which is U equals 0.62. So if U equals 0.62, we know that that equals 1 minus the change in the applied stress. Sorry, the change equals 1 minus the change in the pore water pressure, the excess pore water pressure over the applied stress, which we could recalculate as the change in the pore water. So the change in the pore water, which is the excess pore water, over the change in the total stress would equal 1 minus 0.62, which means that the excess pore water pressure would be 1 minus 0.62 is 0.38, outside of timesing that by the change in the total stress, so change in the stress applied, so 0.38. The question said we applied a stress of 60 kPa, so times that by 60, so 0.38 by 60, we get 22.8 kPa. Okay, so we've now found that the excess pore water pressure at a point when we have 60% consolidation is 22.8 kPa. 22.8 kPa. So this is the excess pore water pressure. And that is at a point when 60% consolidation has occurred. Anyway, guys, hope that helps. Just before I finish, I want you to be very careful that this formula U, which equals 1 minus the change in the excess pore water pressure on the applied stress. So that change in U is the excess pore water pressure, which we found to be 22.8 kPa. Hope that helps, guys.